I'd like to thank the organizers. My name's Nick Chancellor, and today I'm going to be talking about continuous time hybrid quantum computing. There's actually a few different things that are going to come under this topic, which is why I've given sort of a fairly vague and broad title. So let me first mention my collaborators and funding sources. So this is done with a few different collaborations, Viv Candon, Sugato Bose, some of our summer project students, and a grad student at Imperial. And yeah, a lot of it's funded by Engineering and Physical Sciences Research Council, and we'd like to thank D-Wave for giving us time for one of the projects. The main outline of this talk is first, I'm going to give some background on reverse annealing and why you might want to do it, how you might use it for algorithms, then talk about how you might test this. The thing I'm going to argue is, at least for the algorithms here, there's one key feature you need for all of them, which is searching the solution space locally in a Hamming distance sense. And so I do an experiment to show that the actual experimental protocol does this. And then I talk about, rather than hybrid quantum classical, talk about how you might have computations that are actually involving multiple mechanisms to solve the problem. I'll focus on sort of a quantum walk-like mechanism and an adiabatic mechanism that may be acting at the same time, and give some recent numerical data we've got on that. So before going any further, let me just make a note about the language that I'm going to be using in this talk. This is not standardized in the field, so different groups may use this terminology differently. But for the purposes of this talk, when I say adiabatic quantum computing, I mean the closed system version. And when I say quantum annealing, I mean the open system version where there's significant dissipative effects. One of the main reasons I like using this terminology is referring to something with dissipation as adiabatic somehow just feels wrong. So, moving along, why do we want to do this? Why do we want to do hybrid techniques using reverse annealing? And there's a lot of different reasons. It's flexible. You can develop a lot of different algorithms. One thing I didn't put on the slide is there could actually potentially be some ways to gain advantage against misspecification. And I'm not going to talk about that much here, but it is in one of the papers I look at, just very briefly describing how that might work. The basic idea here, as you've already heard, is you actually start out in a classical solution, turn on an annealing parameter to some point where you're actually searching the space around that. I'm going to be focusing on the dissipative version. So these very long searches that Hartmut talked about probably aren't going to be happening in this situation, just because dissipation on real devices will sort of stop that. So that's kind of the difference here. Otherwise, if you just made that ramp back very fast, it would be the same thing. They're two very related protocols. So an example, just a cartoon example of why this might be something interesting, is if you think of an energy landscape with rough and smooth features. If you have a smooth feature where you have a very broad sort of hill, that's going to be very difficult to tunnel through quantum mechanically. But if you have a rough part of your energy landscape, there you could actually take advantage of tunneling. So if you have a broad local minimum, if you just do naive quantum annealing, you'll very often just get stuck there and you won't be able to tunnel through this broad barrier. However, if you use some clever classical algorithm, you may be able to get into a region of your solution space where quantum algorithms can excel. Potentially, even you could just choose solutions randomly, and maybe you get lucky if a significant portion of the space is somewhere where quantum algorithms can excel. Maybe that's good enough. You can do a sort of very toy quantum Monte Carlo example of this. I'm not going to go through in detail, but you can see you can start in a sort of frozen regime. When you turn up the annealing parameter a bit, you can search locally in an area around that. And then if you turn it up too much, you get stuck in a false minimum in this example, which is an example with an engineered false minimum. Later, I'm going to look at an example like this on a real device, a real D-Wave device, and show that you get the same kind of behavior. So one advantage of this, there's a large number of possible algorithms that you could do using reverse annealing. Essentially, this turns a call to an annealer from a sort of standalone algorithm that maybe you could do some post-processing with to a subroutine call, because you now have this initial state that you can put in, and that initial state could be found in some clever or not clever way, depending what you want to do. We saw an example in one of the previous talks of using a greedy search to seed this, but you could do all kinds of other things. For instance, I'm going to talk really quickly about an example of some things you could do, some Monte Carlo inspired algorithms, some genetic algorithm type things, just sort of to motivate why you might want this. So another thing you might want to do is to reverse anneal different qubits differently. To some extent, this may actually be possible with the controls currently on the D-Wave device, but I'm sort of going to be thinking more generally, just for this first bit, talking about algorithms. To represent these different algorithms, I use a concept called an inference primitive. Basically, this purple sort of pentagon you could think of as representing your classical computation, and you represent as sort of a red box your calls to annealers. So you could imagine representing sort of traditional quantum annealing. You just have your problem definition, send it through, and then it goes out the other side, and maybe you do some post-processing. You could do repeated local searches just by doing this over and over again, and actually seeding a state, whereas on the other one, you just define your problem, you don't seed a state. You could also do population annealing and parallel tempering inspired protocols. I'm not going to go through the details on this, but there's ways you can do it. You can even do some sort of genetic algorithms using this idea where you actually, in your classical processing, you're actually feeding in streams coming out of multiple annealers, and then you use that to feed into your local search. Generally, this works better if you have a local search that searches different amounts on different qubits, or possibly different clusters of qubits. There's an archive paper reference there that goes into the details of how you might do this. So, as I mentioned previously, what all of these ideas have in common, at least all the ones I've presented here, the things that the Google group talked about are a bit different, is that they rely on this idea of local search, this idea that somehow you're gaining an advantage by seeding a state into your annealer and seeding classical information in to help guide your search. So a natural question is, does a real annealer, say the D-Wave device, actually do this with this reverse annealing feature? And you can sort of make a lot of intuitive arguments that it should, that when you turn on not so much transverse field, you'll somehow stay local in Hamming distance. But it would be nice to actually see it experimentally. So to do this, what we want to do is generate an energy landscape like the cartoon one there, where we start in a sort of small local minimum near a true minimum, but then we have a broad false minimum somewhere far away. So we can actually construct a little gadget that does this. To start off with, we realize that two of the features we need, this broad false minimum and this lower local minimum, there's actually already gadgets that exist to do this. For instance, this gadget from this Dixon paper. So now all we need to do is engineer this other minimum that's our starting point. So to do that, we just add a coupling between these two. We start in a state that's the ground state, except for we flip that cluster of 4 spins. And by controlling those fields there, we can actually control where our where the unavoided crossing is between the false minimum and the true minimum. So now what happens if we actually run this? Well, what we see that vertical line is where this crossing between the false minimum and true minimum is. So beyond that, the lowest energy state will be our actually our false minimum, because this false minimum quantum fluctuations, because it's much broader, will lower its energy. And this is S prime. This is how far we anneal backward. So we see for certain values of S prime, we just stay in the state we programmed. Well, that's good. If we weren't starting in the state we programmed, that would be very worrying. Then after a while, we tunnel out into this narrow true minimum. If we go back a certain amount, the fact that that tunneling and the avoided crossing are at the same place roughly is probably just a coincidence. I don't think there's anything more that can be read into there. And then we see if we go out too far, if we turn on our S prime too high, we actually get stuck in the false minimum, just like we would in traditional quantum annealing, where you just start from a state of maximal ignorance. And so this gives a very clear sort of proof of principle example that indeed we are performing local search. We are searching in some way locally around our starting state, and that the sort of intuition behind how these algorithms were constructed is actually okay. So future work, we would obviously like to go much beyond this. Apologies to Murray for the diagram on the bottom. I saw him flinch a little bit when he saw it. I agree with your point about this tunneling through hypercubes, but I created this before the conference. We actually would like to look at the range you actually search with problems with known solutions. In particular, look at things like planted solution problems and starting a certain Hamming distance away from them, things like that. But we just got the access very recently, so we haven't had time to do these sort of more advanced experiments. Also testing trade-off between memory and search range, possibly looking at this, if this could be an interesting tool for sampling, where you can try to possibly overcome some of this bias by starting in different states, by feeding in different states. All right, so now I'm going to change direction a little bit. Previously I was talking about hybrid sort of quantum classical techniques and how you might use those. Now I'm going to shift gears and talk about hybrid quantum. So what do I mean by this? What I mean by this is using multiple mechanisms. So in particular, we know that there are different ways to solve certain problems. For instance, the unordered search problem, we know both adiabatic quantum computing and quantum walks can solve that problem. So roughly there's sort of 3 known mechanisms that can solve problems in continuous time. There may be more, but we're going to focus on these 3. There's the sort of quantum walk-like mechanism where you have just a Hamiltonian turned on for some period of time. It evolves, and then you measure out. You have adiabatic, by which I mean closed system adiabatic, and then you have dissipation-dominated type searches like what you have on many real devices and things like that, where you can't necessarily ignore the effects of dissipation. There's been a lot of work already on this sort of access between AQC and quantum annealing, between the open and closed system. What I'm going to be focusing more is thinking about how you might interpolate between AQC and quantum walk. So one thing you can do is you can think about, okay, what happens if we, or can we define an interpolating function where we can actually have things that combine the 2 mechanisms, and we can actually build annealing schedules that continuously go between the quantum walk annealing schedule, which is just you instantaneously ramp to some point, you wait some time, and then you measure out, or optimal adiabatic schedules. We do this for simple search, and what we find is indeed you can gain a root n speed up if you do this interpolation in the right way, for an entire continuum that we parameterize by a parameter alpha. I'm not going to go through exactly how we do this, but there's an archive paper that explains in detail how this works. You can sort of see a diagram of success probabilities, and you can see on the alpha equals 0 side, you have the oscillations that you'd expect in a quantum walk. On the alpha equals 1 side, it looks much more adiabatic-like. One important thing to note is, in contrast to a lot of what other people have looked at, a lot of this is very far from the adiabatic limit. This isn't just looking at what happens if you're in the adiabatic limit and what are your corrections. Here there'll be very strong corrections to the point where you're actually not doing anything adiabatic at all and you're actually just exciting up very strongly into the excited state and to the point where you're actually half in the excited state and doing a quantum walk. With this, it's all very nice, but we'd like to look at more realistic problems than unordered search. And in particular, no one's really thought about what a quantum walk might do on these. And so we want to think about this. The first thing we'd want to think is this even an idea that could vaguely work at all? And you can come up with an argument that there is at least a mechanism to search for low energy states if you do a quantum walk on, say, a spin glass. And the argument you can see here is, by a quantum walk, in this case, I mean starting in the ground state of the driver Hamiltonian and then turning the Hamiltonian on. So this is different from what Google talked about, where you start in a classical bit string. And you can see this argument here. You can divide your Hamiltonian in two parts, the driver part and the problem part. And your energy with respect to the driver part, the part of your energy coming from the driver part, can do nothing but increase because you're already in its ground state. So therefore, if any dynamics happens, the energy with respect to your problem part of your Hamiltonian will have to decrease by energy conservation. So this, at least to some extent, will preferentially seek out low energy states. So our questions we have are, how does this relate to QC, and how effective is this mechanism? One point I'd like to make is you rarely ever in a real system actually know your optimal AQC schedule, and you're oftentimes very far from adiabatic. So even if this isn't very effective, it will probably be a secondary mechanism to whatever you're doing. So you'd better understand how this works, whether you're trying to do it on purpose or not. So let's look at an example. So here I've built a gadget where I can tune the gap. So I know for adiabatic, I can tune the small gap to be later and later, and I can tune this to be harder and harder for adiabatic. I can, in contrast, look at doing a quantum walk on this kind of spin glassy gadget. And I can ask a question of, as I make this harder for adiabatic, as I make the gap smaller, does it get harder for quantum walk? And I can actually make the gap quite small by making the two in states almost degenerate. And what you can see is a rough calculation of runtime adiabatically by just calculating the gaps. I change by 13 orders of magnitude, and more like 24 orders of magnitude if I don't know how to construct an optimal AQC schedule. But if I use a quantum walk type mechanism, I actually increase in performance by half an order of magnitude. So of course, this is a very artificial problem, but the point here is this doesn't depend on gap in the same way that adiabatic does. So you have something where you may have a very small gap, but in that case, you may have a secondary mechanism that gets you around that. So the next question, we know search with a quantum walk, there's this parameter gamma, the strength of your driving. And there you have to very fine tune it, which for something like an optimization problem, you may not know what that fine tuning is, and you definitely would have control errors, so you wouldn't be able to. So the next question we ask is, how sensitive would your success probability, here we just calculate long time success probability, be to this parameter gamma? this parameter of how strong you put your driver on. And what we can see here is actually it doesn't seem to be vary for, in this case, a Sherrington-Kirkpatrick spin glass. So that's sort of another indication that this is doing something interesting that's different from AQC, and that thinking about this kind of mechanism could be an interesting thing to think about even on a more realistic problem like a spin glass. Of course, the million-dollar question is how well this works, which I'll touch on a little bit. We have some preliminary scaling results, but we're still trying to answer that question a bit. As I pointed out before, even if the answer is this doesn't work very well, this is likely going to be a secondary unwanted mechanism that may be helping you solve your problem, just because you're probably not going to actually be adiabatic in many cases. You may have a very, very small gap, and you may just not be able to go slow enough, or many very small gaps, or a small avoided crossing that involves many levels. So you may actually inadvertently be having these kind of effects. So understanding, thank you, how well quantum walk works on these kind of problems is, on spin glass problems or more realistic optimization problems, is worth doing, because you can imagine some mechanism like that being important. Here's some preliminary results for looking at scaling on a Sherrington-Kirkpatrick spin glass. I actually have a little bit of random energy model curve there. I'll talk about that a little bit later. And you can see that we've looked at two parts. One is equilibrating, and the other is what success probability do you reach, so you can repeat. Both of these actually scale exponentially, but that's not necessarily a problem, because for any hard problem, the performance of your algorithm is probably going to scale exponentially. Otherwise, P is equal to NP, which it probably isn't. So you can see if we add these, if we add the sort of positive gradient on the rough equilibration time to the sort of negative probability gradient, if we're doing a repeat until success strategy, we get something roughly like 0.7. So this would be sort of the end. So like sort of a 0.7 to the n, which, or sorry, 2 to the n to the 0.7, which looks like it could be interesting. Again, these are very preliminary, so I wouldn't trust them too much. In particular, we're trying to come up with a better definition for equilibration time. The other thing is, in the real world, you may not want to wait till your system equilibrates. You may want to measure out before you equilibrate. So you could actually potentially do better. And so I just wanted to show this to show that how this actually scales is something we're thinking about. We just don't have necessarily super conclusive results yet. So a quick aside, I talked about a spin glass. If we look at a random energy model instead, what we find is that we are very sensitive to the strength of our driver Hamiltonian. So we're doing this fixed driver starting in an equal positive superposition of all states, so the ground state of our driver, but also having a problem Hamiltonian turned on to some extent. And you can see here we have both the success probability, and we've sort of plotted the energy levels on the same plot with a different scale. You get something which looks very much like a single avoided crossing in a random energy model, but for a Sherrington-Kirkpatrick, you get something else. Something involving a lot of energy levels is going on, and something we don't quite understand yet. This REM result is probably quite related to some of the things Google was talking about earlier with these sort of longer range tunneling within energy bands, where they're talking about something that looks a lot like a simple search. But the point is, these behaviors are quite different, and probably this has to do with the correlations in energies in something like a Sherrington-Kirkpatrick model versus not for a random energy model, because random energy model, the energy as a function of Hamming distance you go away is just going to be random. It's not going to have any structure at it. We know there's a phase transition as you go to 3 local rather than 2 local, like the Sherrington-Kirkpatrick. We're working on 3 local spin glasses, but we don't have any results for that yet. And finally, we want to test this quantum walk type mechanism on problems known to be hard for AQC. We'd like to thank Elizabeth Cresson for providing us some set of hard max 2-sat problems that are hard for AQC, which we are going to test these quantum walk type searches on and see if, compare those to just random instances and see if the same kind of features that defeat AQC also will defeat a quantum walk, and watch the space. We'll be doing that, and I believe that's time for me.
Do we have any questions for Nick?
So in your comparison, AQC and random walk, a quantum walk in the middle, where you talked about the minimal gap.
Yeah.
Could you repeat the summary of, or the conclusion of this? So did you say that for the quantum walk, the minimal gap was not the decisive
Well,
property?
so in this case, in this one constructed problem,
This one,
yeah, which we've constructed, it's based on this gadget in the Dixon device, but we symmetrized it a bit so that it would be easier for our numerics. And in this case, yeah, the gap, we could tune the gap. We built one where we could tune the gap. Basically, the way the gap's tuned is by changing the fields on those core spins. And what we found in this case is that, yeah, the gap doesn't seem to be relevant in this for what's going on here. So this tells us sort of that this is using a different mechanism than when you're solving unstructured search with a quantum walk, where obviously the gap does matter quite a lot, and it's sort of the deciding factor in your time. Here, there's something more complicated going on, where you're exciting mini energy levels, and you're somehow traveling through them in a complicated way. And in this case, it looks like what the minimum gap is and what's going on around there doesn't make a lot of difference. I mean, we've sort of got this half an order of magnitude effect. Basically, what we did here is we ran for some sensible amount of time and then converted our success probability into a time to success. And so effectively what this is saying is if we change if we do this tuning that increases the gap, or the minimum gap, it doesn't seem to be doing much to our quantum walk. So yeah, hope I answered the question.
Are there maybe one more quick question? Oh.
I think in the quantum random energy model, there's a phase transition from a paramagnetic phase to a spin glass phase. Is that avoided crossing-like behavior associated with that phase transition, or is it something within the spin glass phase?
Potentially. This is something we haven't looked into that much. We just ran the numerics and saw what happened. Someone who knows more about spin glasses than I do could probably tell you, or could potentially tell you. The rough intuition I have about this is if you flipped your definition of your driver Hamiltonian and your problem Hamiltonian, the random energy model would look very much like a fully connected graph. And so it's like, if you view it in that space, you have a very simple Hamiltonian, which is your driver Hamiltonian, which is one local, and then you're searching on that with basically a fully connected thing with some random amplitudes and phases. And that looks very much like simple search. And so that could be why you're seeing this. Again, I'm not really a spin glass expert. Someone who is could probably tell you maybe exactly why we see that.
Let's thank Nick again.